Module 3.4, Applications of MD in Mechanical Engineering. So in this module, we'll learn about how to install MD software such as LAMPS. We'll simulate one-dimensional and three-dimensional Lennard-Jones fluid. We'll have an example of tensile test of aluminum and tensile test of polyethylene chains. Installations for each software such as GROMACS or LAMPS and so on, they have provided very detailed instruction how to install it on different operating system such as Linux, Windows, and so on. And you can follow them to install on Colab or on your personal laptop. So actually, I would recommend to install LAMPS and GPAW if you can, and if you can let me know what are some of the challenges you face during the installation, we can discuss about it. But I have seen personally that a lot of researchers and engineers have problem installing such softwares with all the capabilities. So one of the robust packages for installing software is Conda at anaconda.org. There are others such as Docker, Nix, Singularity, and so on. And all these software platforms are trying to have more robust way to install packages across different operating system, available hardware, and so on. But Conda is pretty robust. So that is what we are going to use in this module. And you can see that Conda module of LAMPS is downloaded about 1 million times. So it's a very popular software. So we'll start with a Lennard-Jones potential. This is a very basic but still powerful way to understand molecular dynamics simulation and how the potential look like. So in Lennard-Jones potential, you have two parameters, epsilon and sigma. So epsilon represent the depth of the potential, and sigma is distance at which the potential is zero. So here we have assumed it to be 1 and 0. And this is the Lennard-Jones potential given by the Python function def Lennard-Jones for epsilon sigma over r to the power 12 minus sigma over r to the power 6. And then since we are simulating in 1D case, one-dimensional case, we generate a r or this or position at 0.8 to 3, and you can change it to whatever you want. And we will use the interval of and total length of 500. Then we can generate a potential using the V, and then we can plot how the V vary over distance. So this is an example how to get V in a single 1D. It's actually a good toy model to understand Lennard-Jones. Now, if you want to simulate this in a 3D case, then you might want to use LAMPS for efficient calculations. So in LAMPS, you have different type of structure or how to give your information in LAMPS. So one of them is LAMPS input file. So in a typical LAMPS input file looks like this. So usually you have a units such as Lennard-Jones unit and so on, or real units, metal units, and so on. So as you can see on the right-hand side, for each of the commands, LAMPS has provided a very detailed description. So you can see on the right-hand side, unit style, the unit can be Lennard-Jones, real or metal or SIs or CGS, and so on. And they'll provide you the description how and when to choose particular unit system. Usually we use the metal unit system unless we are simulating something like Lennard-Jones and so on. And usually you can convert from one unit system to another unit system. Atom style could be atomic, where you have provided fully atomic description, but it could be some other description as well. In LAMPS, there are builders for atomic structure as well. So you can load atomic structure from a pre-existing file, or you can construct a lattice or a crystal structure inside LAMP script. So here we are generating a face-centered cubic lattice with 0.8442 lattice constant with 0 to 20, 0 to 20, 0 to 20, x, y, z dimension. And then we randomly create a velocity to maintain a 1.4 Kelvin temperature. You can vary it as well. And then we use a pair style. So this kind of force field that we want to use. There are hundreds of force field available in LAMPS. Here we are using LJ cut force field with certain parameters. And we talked about the time step. We take 0.001 as femtosecond time step. Thermo is the how often we want to print the simulation result, that is thermo. Neighbor list is basically how often you want to update the neighbor list. When you construct the when you run the molecular dynamics simulation, you have to construct the neighbor list. So it basically tells you how often to construct the neighbor list. We are using NVE ensemble, so we discussed about that, and how many times step to run it. So 1,000. So basically, it will print you 10 times because it's gonna have print the output at every 100 steps. So you'll have 10 outputs at the interval of 0.001 time step. So once you write this kind of SLAM script, we can call it a file such as ljfluid.in, and then we can give a LMP, which is an executable, and -in is the input, and this file that we have saved the data or saved the input description. And this will run the LAMPS on your particular laptop or a cluster on the Colab. So you can see the full script on the Google Colab notebook, so don't worry about that. You'll have a very hands-on experience of how to run LAMPS. So because Python is so popular in multi-scale modeling and modeling in general, LAMPS has also developed PyLAMPS, Python wrapper for LAMPS. So this allows you not just write things in text, but also give a command line, but also have a syntax-based input for LAMPS. So you can initialize the PyLAMPS, is kind of empty object that we learned in the coding class. Is an empty object, and then you start adding units, atom style, lattice, and so on that we defined. So you can see these are basically the same information we wrote in the previous slide, but just in a Pythonic way, in a way we can call it. We can also visualize the structure. So these are FCC 2020 lattice, Lennard-Jones lattice, and then we are running NVE, so energy should be constant. So if you run 1,000 steps, you can see the time steps are 1,000. We can see the energy is almost conserved or constant, which it should be. So this was quite ideal system for simulating something realistic like aluminum. We can also initialize it with units metal. It's a 3-dimensional system. It's periodic in X, Y, Z direction. That's given by PPP. In some cases, suppose you want to simulate a surface, then you have will not have a periodic boundary condition in Z, for example. Let's call a variable, let's define a variable called lattice parameter, which is 4.04. So remember, we got this 4.03 or 4.04 in our DFT calculations. So now you can actually vary this lattice parameter for a particular material as well. And then we can construct a force face-centered cubic 10 by 10 by 10 lattice of aluminum. And then we can call this region hole, and we can assign a pair style or force field like EAM, embedded atom method for alloy is one of the force field which is implemented in LAMPS. And we can assign pair coefficient. So remember, in the previous slide, we had the pair coefficient as actual numbers, but because we have aluminum, which is more complicated, we provide the actual file for the entire file for aluminum force field. So these files, you can get it from the NIST website or some others. So here we are trying to develop from the NIST website, the aluminum Zhao potential. And then before running MD, we can kind of equilibrate the system or kind of relax the system to reach its minima. So we are trying to run NVE with Langevin thermostats with particular damping factor that we talked about. And then we can deform the system. So in LAMP, there's something called fix all deform. So we talked about units command, dimension command, variable command, a lattice command. There's also something called different fix commands. So fix allows, for example, NPT, NVE. Also have a deform command, so you can provide the strain rate, how fast you want to strain the system. Usually the strain rate are way faster than experiments. So just because we cannot reach the experimental level, we use a very fast deformation mechanism. And then we can have outputs. So you want to have output in gigapascal. So LAMPS give you PXS, which is the pressure in XX dimension. You can divide that by corresponding unit conversion to get gigapascal. You can ask LAMPS to how often print and what to print in a particular file. So you'll be solving the equation and storing the data in trace strain txt file. And we can also dump movie. So you can dump the movie like LAMP's trash file, and you can visualize in software such as Ovito. That might be one of the assignment I'll give you to visualize the movie and see how the atoms move. It's pretty fascinating. And you can also kind of say how often or how long to run the simulation. So these are some of the input file for aluminum. And after you have run the simulation, you can get the stress strain output that we just printed from the previous step, and you can get the stress strain curve. So you can see the very similar to what we did in DFT, but here, remember, we are at a regime where the things will break, right? So there you'll see it will deform elastically, then there's a yield, and then definitely it will deform plastically. That means it will not come back to its original position. And because we were giving the strain in x direction. So remember, we provided the all deform in x direction. That's why you have stress in only in x direction, and the y and z components are almost nil, right? So you can also change it to be in y and z, or have x and y both if needed. So that was a case of solid like crystalline aluminum, but we may also want to simulate polymeric system. And then we have force fields such as AI Rebo, Druiding, Meme, and there are various type of other force field in Amber, Charm. So here we are going to use the Meme potential. So as we said, we will load the data instead of creating the structure from a FCC constructor. We'll load the data from a polymer.data file, which I'll provide in the Google Colab notebook. And then we'll have the force field meme modified embedded atom method, and we'll have certain Pierre coefficient or force field parameters. As we said before running MD, we equilibrate or minimize the lattice position to kind of reach its minima and use NVE and Langevin. And then we can have deformation. This is the alternate way of deforming crystal. So you can have groups of the box where you want to apply the strain. You may not want to apply strain on the entire block. You might want to have something like a dog bone test in the tensile experiments. So you want to have particular place where you want to have the strain imposed, and then you can run the simulation. So in this case, we are using Meme potential. We are minimizing the crystal structure before we perform a tensile stress, and then we can have stress per atom as the visualization. As you can see on the right-hand side, the movie is being visualized. So there are many other examples out there. So I have provided some of the links there. So LAMMPS has nice tutorials. It has also some benchmarks. So I always ask students if they have time to run some of the benchmark problems. So before doing any modeling, it's important to have benchmark or validation with experimental data or available theoretical data. So it's good to have some of the benchmark problems available in LAMMPS itself. And there are many other tools such as lampstutorial.github. There are several movies collections from LAMMPS, so which is quite interesting as well.